Welcome to Earthly Teachings. In this detailed tutorial, we'll be diving deep into Electrotechnics N4, focusing on the fundamental principles of three-phase induction motors. By the end of this video, you will be able to, first, define what an AC machine is and understand the basic concept of an induction motor. Second, you'll be able to identify and explain the various parts of a three-phase induction motor. Third, we will compare and contrast the two main types of rotors, squirrel cage and wound rotors, discussing their construction, advantages, and disadvantages. And finally, we'll explain the common star and delta connections used for stator windings. This lesson is designed to be your comprehensive guide for exams and future studies. So, let's get started. First, let's establish our foundation. What exactly is an AC machine? An AC machine is any rotating electric machine that converts electrical energy into mechanical energy, or mechanical energy into electrical energy. When it acts as a motor, it takes electricity and produces rotation. When it acts as a generator, it takes rotation and produces electricity. The motor we are focusing on is an induction motor. An induction motor works on the principle of electromagnetic induction. It produces torque, or rotational force, through a clever interaction. A rotating magnetic field is generated in the stationary part, the stator. This field induces currents in the rotating part, the rotor. The interaction of the stator's magnetic field and the rotor's induced current is what makes the motor spin. A key distinction of the induction motor is how it powers the rotor. Unlike DC machines, the rotor of an induction motor has no direct electrical connection to the supply. It gets its current entirely by induction from the stator. This is why it's called an induction motor. The current in the rotor is induced. And why do we use these motors? Three-phase induction motors are incredibly popular in industry because they offer many advantages. Let's look at a few. They are self-starting, meaning they don't need any special help to get going. They have a very simple and robust construction, making them reliable and requiring little maintenance. This simple design also makes them relatively cheap. They are also very efficient, come in many sizes, and produce a high operating torque. So, to recap this scene, we've defined an AC machine, learned the principle of an induction motor, and understood why three-phase induction motors are a cornerstone of modern industry due to their many advantages. Next, let's explore the structure of a three-phase induction motor. We'll be looking at Figure 5.2 from your notes to visualize each part. Here's a cutaway view of a three-phase induction motor. Let's identify the main components. The motor's outer casing is called the stator. It's stationary, as its name suggests. Inside the stator is the rotor, which is the rotating part. The shaft of the rotor is what connects to and drives the machinery. The end shields, or end bells, hold the stator and rotor components together and protect them. The shaft is supported by bearings, which allow for smooth rotation and minimize friction. For larger motors, a cooling fan is often mounted on the shaft to prevent overheating. Electrical power is connected to the terminal box, which contains the connection points for the stator windings. The stator windings are the coils that generate the rotating magnetic field. So, to summarize this scene, we have successfully identified the major parts of a three-phase induction motor: the stationary stator and its windings, the rotating rotor and shaft, and the supporting components like end shields, bearings, terminal box, and cooling fan. Now let's examine the two main components in more detail, starting with the stationary part. The stator. The stator is the foundation of the motor, the stationary part that holds everything in place. It consists of three key parts. First, the stator frame. This is the robust outer casing, usually made of die-cast iron or steel. Its purpose is to provide mechanical protection for the entire motor and to support the internal parts. Second, the stator core. This is where the magic happens. The core is a laminated structure made of many thin steel plates, each electrically insulated from the others with varnish. This lamination is crucial because it minimizes eddy current losses, which would otherwise reduce the motor's efficiency. Third, the stator windings. Also called field windings, these are the three sets of coils inserted into slots cut into the circumference of the stator core. When a three-phase AC supply is connected to these windings, they produce the main rotating magnetic field that is essential for the motor's operation. So, to recap, we've broken down the stator into its frame for protection and support, its laminated core to minimize eddy currents, and its windings that create the vital rotating magnetic field. These parts work together to set the motor's rotation in motion. Now let's turn our attention to the heart of the motor, the rotating part, the rotor. There are two main types of rotors we'll study. The first is the squirrel cage rotor. This is the most common and robust type. It gets its name because its conductive bars, when connected by end rings, look exactly like a squirrel cage. Let's look at its construction. It consists of a laminated steel core, similar to the stator core. Slots are cut into the circumference of this core. Solid copper or aluminum bars are inserted into these slots. Importantly, the slots are slightly skewed or angled relative to the shaft. This skewing reduces magnetic noise during operation and helps to produce a smoother, more even rotation. At the ends of the core, the rotor bars are short-circuited by two solid end rings, which act as conductors. Because the bars have a large cross-sectional area, they produce a very robust rotor with very low resistance. This construction leads to several advantages. Squirrel cage motors have a simple, robust construction, require no maintenance, and have a very long lifespan. They produce a smooth and silent operation. They are used in countless applications, from fans and blowers to lathes and other machinery. However, there is a challenge. The very low rotor resistance means the starting currents are very large. Because of the cage's simple short-circuited design, you cannot add any external resistance to the rotor circuit to control these currents or the motor's speed. We will deal with how the rotor gets its current and how to manage these challenges in a later lesson. For now, remember its key features: skewed bars, end rings, and low resistance. To introduce the second rotor type, we first need to quickly review the concept of three-phase connections. Three-phase AC systems can be connected in two main ways: star or delta. Let's start with the star, or Y, connection. As you can see, the starting or finishing ends of the three coils are connected together at a common point called the star or neutral point. The other ends are then connected to the three live conductors. Next is the delta connection. In this configuration, the opposite ends of the coils are connected together to form a triangle. The end of each coil is connected to the start of another. The three wires are taken out from these joints. A key difference from star is that there is no neutral point in a delta connection. Understanding this is crucial for the second rotor type. To recap, star connects one end of all three coils together, forming a neutral point. Delta connects the coil's end to start, forming a closed loop with no neutral. Now that we've covered the connection types, let's look at our second type of rotor, the wound rotor. Wound rotors are also known as slip ring rotors or phase wound rotors. They are built differently to offer more control over the motor's starting characteristics and speed. Similar to the squirrel cage rotor, it has slots in its circumference, and these slots are also skewed. However, instead of solid bars, this rotor contains a three-phase winding, just like the stator. These rotor windings are always connected in a star configuration. The ends of these star-connected windings are not short-circuited internally. Instead, each end is connected to a slip ring mounted on the same shaft. Now let's see how these slip rings allow for external control. We'll look at Figure 5.6. Here we see the internal star-connected rotor winding, and its ends connected to the three slip rings. Brushes, typically made of carbon, make contact with these rotating slip rings. These brushes then connect the rotor windings to an external star-connected rheostat. This rheostat allows us to add or remove resistance from the rotor circuit while the motor is running. This gives us several advantages. With a wound rotor, we can produce a high starting torque, limit high starting currents, and even control the speed of the motor by simply adjusting the external resistance. As the motor develops speed, the resistance is gradually reduced. At full speed, the slip rings can even be short-circuited, making the wound rotor behave much like a squirrel cage rotor. These advantages make wound rotors ideal for heavy-duty applications where high starting torque and speed control are critical, such as driving hoists, cranes, and elevators. So, to recap, the wound rotor's key features are its three-phase star-connected windings and slip rings that allow for external resistance, providing high starting torque, limited starting currents, and speed control. Let's quickly cover the final components of our motor. First, bearings. As we saw in the full motor diagram, the rotor's shaft is supported by bearings, one at each end. Their essential function is to support the rotating rotor and minimize the friction between the moving and stationary parts, ensuring smooth operation and extending the motor's life. Next, the terminal box. This is where the motor receives its electrical power. The terminal box is located on the stator frame and contains 6 electrical connection points for the 3 stator windings. The main cable from the power supply connects to this box. The way the stator windings are connected inside the terminal box determines whether the motor runs in a star or delta configuration. As you can see in Figure 5.7, for a star connection, a bridge piece is used to connect the 3 ends together. For a delta connection, the ends are connected in a loop to form the triangle. We have now covered the bearings for smooth rotation and the terminal box, which provides the electrical connection and allows for star or delta configuration. These components are vital for the motor's function and connection to the power grid. Finally, let's recap everything we've learned in this detailed tutorial on 3-phase induction motors. We started by defining an AC machine as a device that converts electrical energy to mechanical or vice versa, focusing on the induction motor where the rotor's current is induced, not supplied. We then disassembled the motor, identifying its key parts: the stator, rotor, end shields, bearings, and terminal box. We took a deep dive into the stator, composed of the frame, laminated core to reduce eddy currents, and stator windings that create the rotating magnetic field. We compared the 2 rotor types: the robust and maintenance-free squirrel cage rotor with its skewed bars and end rings, versus the wound rotor with its star-connected windings and slip rings, which allows for external resistance to control starting torque and speed. And finally, we reviewed the crucial star and delta connection methods that can be applied to the stator windings within the terminal box. Mastering these concepts provides a solid foundation for more advanced topics in Electrotechnics N4. Thank you for watching Earthly Teachings. We hope this video has been helpful for your studies. Please subscribe for more Electrotechnics N4 tutorials and revision lessons. See you in the next video. Osha.